or something to figure out like what I'm trying to ask. But I just want to know, like, what do you guys think it means when I have a high activation energy? And so if you have your graph, right, this is your graph, and this is your energy, and this is time, okay? What would it look like for a reaction? This is our products, and these are our reactants. What would it look like for our products to have a really high, or backwards, this is backwards. What would it look like for our reactants to have a high activation energy? Well, it's going to be extremely tall, right? And then do you want it to be exothermic or endothermic? Endothermic, let's say. So it's going to go like that. So this would be your activation energy, all of that. And it's going to take a lot to climb that hill, and that's why it's really hard to have spontaneous reactions when you have a high EA. Draw a graph of the same reaction, but with an introduction of a catalyst. So now I'm trying to figure out what you think a catalyst is, and how does that affect the EA. So what do you guys think a catalyst is? Right, I like that. It creates a new pathway that has a lower activation energy. So even though there's more steps, it takes less energy to get from point A to point B. So it looks something like this. You have a little bump, another little bump, and then be right there. And so like it's smaller. And so you have more steps, intermediates, but it's easier. Question, is the catalyst consumed in the reaction? No, good. I asked that once in a SI session and people said yes, and I was very sad. I almost cried, but I didn't. But no, a catalyst is never consumed in the reaction. It always stays in the end, and so you can reuse it. Draw a basic equation of a reaction with a catalyst. Basically, I just wanted you to be all like, I have reactants plus catalyst equals products plus catalyst. And just to reiterate that they are not consumed, because that was a legit question on my exam, and so I'm emphasizing those parts. Yeah, anyways, okay, so things to note. What is an intermediate? Like on our graph, we have drawn a different, let's draw another graph up, and then let's go like this. Okay, so what would our intermediate be? Would it be at 1, 2, or 3? Our intermediate would be at 2. This is our intermediate. Our intermediate is the place in between the products and the reactants that we settle. It's stable at this point before it reacts again. 1 and 3, what are they? These are our transition states, and these are not very stable. They're moving, they're still changing bonds. Everything's kind of really crazy. These are our transition states, and that's something to note. Oh, I forgot to go over. We should do this one really quick. Okay, termomolecular, bimolecular, and unimolecular. Which ones are they? So for this one, what kind of molecular is this? It's sorry, go back to number 19, I'll wait for you. 1, 2, 3, time's up. Okay, so x, y squared, is that unimolecular, bimolecular, or terramolecular? Terramolecular. Terramolecular means how many particles, pieces are interacting at the same time. You have, thank you. Keep doing that. It's awesome work. You have 1 x and 2 y's, so it's termomolecular. This one's bimolecular. The y goes away because it's equal to 1, so technically your rate law is equal to k concentration of x, and then that's unimolecular, if that makes sense. Just know what those definitions mean, termomolecular, bimolecular, and unimolecular, because I don't know, unimolecular, U-N-I, like unicorn, but molecular instead. And that's, just know how to recognize those. 21. Okay. For the decomposition of N2O4 at 250 degrees Celsius, the rate of the forward reaction, the rate of the reverse reaction are, I give 2 numbers respectively. What is the equilibrium constant for the reaction given between those two? So what do we know about how to solve this kind of crazy, right? Okay, we know we have equilibrium constants involved, which is our K, and we're given the rate. So we're looking for the K of equilibrium, and we're given 2 Ks, right, for the forward and reverse reaction. We know We know the temperature, and we should know the concentration. So, okay, what are we going to do? The rate for, let's do N2O4 to 2NO2 is Kf, which is the forward reaction, right, times by the concentration of N2O4, and then what exponent does it have? This is equilibrium, so usually we would not use our coefficients, but this is equilibrium. So we can do that this one time, and it gives us a coefficient. It gives us an exponent of 1. If it's not, we're not dealing with equilibrium, don't do it. It's bad. But in this case, it's okay. So it gives us a coefficient of 1. The next one would be the reverse reaction, right? So it would be rate is equal to your K of R, and then NO2. What exponent does it have? 2. So notice that our rate for the reaction should be the same. So technically, if we wanted to, we could go K of F is equal to N2O4 equals KR NO2 2, right? And then we want to find what? We want to find our equilibrium. Well, we can find our equilibrium for the reaction if we move, yes, thank you. We can find our K of equilibrium, or KE, if we move our K's over to one side. So if we divide both sides by KR, and we divide both sides by this, N2O4, because you want it to go away, what are we left with this crazy math that I didn't really design very well? So it would be KF over KR, because they don't cancel out, equals these two cancel out like these two do. So you get NO2 times by to the power of 2, N2O4 on the bottom, right? We know what, excuse me. Pardon? Why would we divide it over? Because in the book it has it where, like, if you divide your equilibriums by each other, then they become if you divide your K's by each other, they become the equilibrium K, if that makes sense. It's one of the definitions in your book that you should know. No, because if I square KR, I don't understand your question, I'm sorry. Oh, I see, it's the math, I'm sorry, I wrote that wrong. Yeah, so I understand, good question. So she's asking, okay, so we have KF, and then N2O4, but I want to move all my K's to one side, right? So I move my KR by dividing it. Oh, thank you. I move my KR by dividing it on both sides. And then I have KF over KR times by N2O4, and then NO2 squared. And so, yes, is that better? And so then I divide both sides by N2O4, and then I get KF over KR equals NO2 squared N2O4. Does that answer your question? Okay. 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 So yeah, we do that. We would plug in our KRs and KFs and KRs, because this value is equal to our K of E, which is what we're looking for. Sorry, move it up. I caught myself. So KF divided by KR is equal to our K of E. So we don't really care about our equilibrium, concentration, whatever. It doesn't matter in this case. So our KR is, KF, 1.3 times by 10 to the 2, and our KR is 3.2 times by 10 to the negative 2. And you'd want to do the math for that. Times by 10 squared divided by 3.2 times by 10 to the negative 2. Move it up more. Okay. And I get, really? Okay. I get 0.406-ish. Does that make sense? Any questions? Well, I guess scratch paper. No? Okay. So that would be your new Ke, your Ke. What? Yeah? Maybe I did it wrong. Let me do that again. Oh yeah, you're right. I did do it wrong. There you go. So this is not, it's 12. I forgot to put the parentheses. I didn't close those. Always close your parentheses. So 12.69-ish. Round up. Oh. Oh. Really? So that equals divided by 3.2 times by 10 to the negative 2. Syntax. I hate syntax. Okay. That one. Okay. Yeah, you're right. So it'd be, don't, I know my math is bad. I'm sorry. I try. Okay. This is what you will get. I promise. You're all good, right? Okay. Y'all got the same thing? Okay, good. Just checking. Just checking. Okay, next one. Acids and bases. How much time do I have? I have time. Okay. Give an example of an Arrhenius acid and base. Give an example of a Bronsted acid and base. Give an example of a Lewis acid and base. Know your bases. Okay, if you're going to organic chemistry, know your bases. If you're going to take this test, know your bases. Know your bases. I can't stress it enough. Oh my gosh, know your bases. Okay, Arrhenius. Let's just define what they are, and then we'll move from there. So Arrhenius acid, Arrhenius, right? Acid and base. Well, what does an acid, Arrhenius acid do? It produces, right, it produces H plus ions, and that would be our acid. And then what would a base do? Right, it produces our OH ions, and that's our base. Examples of that would be, let's do, I have this one. This one works good. So it'd be HCl plus NaOH. What does that yield? Right, water and NaCl. Or if you just want to split up the ions, you'd have your H plus, Cl minus plus Na plus, OH minus. So you'll notice your HCl produced an H plus and your Cl negative, right? We're saying that Arrhenius acids produce H plus ions. So we know that hydrochloric acid is an acid, right? And what does it produce? H plus ions. And so that's kind of what it's talking about. You can't see it with just the net reaction, but if you take apart the ions, you'll notice that your bases produce OH negative hydroxides. Bronsted-Lowry. Bronsted-Lowry. Acids, what are they? Excellent. Proton donors. I had like an acronym, I had like PDA in it, but I forget what it is exactly. It was stupid. But if you can have an acronym, is my point. Get an acronym, even if it is silly, then it'll help you remember it on the exam when you're like, I forgot if they donate or accept protons. And since acids donate protons, you know, your bases accept protons. Accept protons. Okay, so examples of that would be, let's do HCl and water, right? HCl plus H2O. We yield H3O plus Cl negative. Where did the water go? This guy accepted the proton, right? Which means it had to lose it. If it accepts equivalent exchange, right? To accept something, you have to give up something. If it accepts the proton, what's it giving up? It's giving up its electron. So if your water is giving up its electrons, then it is a acid or base. And that makes sense because we know HCl is an acid, which means it is oh wait, we're not doing electrons yet, never mind. Proton accepting and donating. Okay, so proton donors, which one's donating the H? The Cl, so it's going to the water, and the water's accepting the proton. That makes it so much easier. I'm like, why did I use this example? It's so complicated. But that's because it's about where the proton goes. The proton is being accepted by the H2O, and so this is a base, and this is an acid. And we will move on now, because I'm just making it more complicated. Acids. Okay. Lewis acids and bases. I already said it. Is it electron donor or electron acceptor? Electron acceptor. So electron acceptor, which means our base is an electron donor, right? Examples. I don't know if I want to do examples. Okay. Let's do H2O. Yeah, we'll do the same example because it'll help clear things up. Yes, thank you. HCl, and then that yields an equilibrium, HO, H plus Cl, and then it's negative, so it has all these electrons. Okay. So what do we know that goes on? We know that from our Lewis acids and base definition, that our acid is going to accept electrons, right? So, yeah. So our electrons are going to go over and grab that hydrogen. It donates its electrons and gives them to chlorine. So now chlorine has, you'll notice, one too many electrons because it stole them. And so, therefore, it's hopefully a little bit makes sense that these guys donate their electrons to the hydrochloric acid. Okay. You would have to find a really strong acid. And then if you had a really, you need, acids and bases is really relative. It's like calling someone beautiful. Well, beautiful is compared to what? Something tastes delicious, but if you've only eaten bugs the rest of your life, then mold's going to taste awesome, but it doesn't mean that you should actually eat it. So acids and bases are the same way. Water acts as an acid or a base. What's that called? Amphoteric. When water acts as an acid or base, it's called amphoteric. And so hydrochloric acid could possibly do the same thing if you had an acid that's way more acidic than hydrochloric acid. But I don't know of one. If it was, it's probably really unstable. But I mean, theoretically. But you won't see that. That'll be if you're a chemistry major, then you'll see it. And then I'm sorry, I'll pray for you. Determine the base acid, conjugate base of the reactions below. Okay, so let's just focus on these guys first because that'll make the rest of it easier, right? So move it up and over. H2SO4, sulfuric acid. Is that an acid or a base? It's an acid. And then we know that why? Well, what's it doing with its proton? It's donating its proton. And so we know that from Bronsted-Lowry, it is an acid. It's also accepting what? It's accepting electrons. And from Lewis, what do we know? Acids accept electrons. And so if this is our acid, then this must be our base. And so then it's really easy because all you have to do is, if this is an acid over here, then our sulfuric acid is now our conjugate base. It's always the opposite. And then here, our base now becomes our conjugate acid. Easy peasy. Let's do this next. I'm not going to give it away this time. Okay, we have HCO3 and H2O. So where are our protons going from here to here? It's gaining a proton. So it's stealing a proton from water. If it's accepting a proton, that makes this a, yes, sorry. Okay, if this needs a proton because it has two over here, right? If it's accepting a proton from the water, then this is a base. And if this is giving a proton, then this is a acid. Notice our water, basic, acid, fun, right? Okay, so if this is our acid here, then that means over here our OH negative is our conjugate base, and that means that this carbonic acid is a conjugate acid. Obvious, easy peasy. Backwards, reverse. Okay, this one and this one. Is this accepting or donating a proton? It's donating a proton. Proton donors are acids. And then this would be our base, et cetera, so forth. I don't need to continue, do I? No? Okay. Next page. Easy peasy. Acids and bases are fun. They're more fun later, though. Right now, they're just kind of torturous, but later they're fun. Okay. In the reaction between ammonia and boron trifluoride, which acts as a Lewis acid and base? No, this is page 4. Okay. Let me go up. 1, 2, 3, 4. Okay. So in the reaction of ammonium and boron trifluoride, which acts as a Lewis acid and base? So we got to figure out which one does what. Ammonia, what's that look like? You should know that, hopefully. H plus boron, B. Trifluoride, how many fluorides do we have? 3. 1, 2, 3. F. Any lone pairs on the boron? No. Why? because it's an exception. It's one of those, from Chem 1A, you had like a bunch of exceptions, one that had way more than an octet and one that had way less than an octet. This is one of the ones that are way less. I would know those. Like, I would figure out which ones are exceptions to the octet rule. And then we don't really care what it yields. In the reaction, though, what's it going to do? Which one's going to accept electrons? Well, which one has electrons to give? The ammonium has electrons to give. The electrons are going to go over here and do something. So if this is donating electrons, then is that a Lewis acid or a Lewis base? It's a Lewis base, which makes this our acid, and that answers our question, so we're done. Excuse me. Okay. Next one. 24. Okay. Define the following as diprotic, polyprotic, or monoprotic. And this is kind of a trick question a little bit. HCl, right? Can you see that? Yes, you can. Okay, so HCl. Is that diprotic, polyprotic, or monoprotic? Monoprotic. Mono. HBr. Monoprotic, diprotic, or polyprotic? Okay. How about a trick question? HClO4. Monoprotic, polyprotic, or diprotic? Mono. Maybe not such a trick question. H2SO4? Di. And then CH3COOH? Mono. Why? Because this is the only one that can be like donated. The other H's are very happy on their carbon and they don't want to leave. So they're not really going to leave, and so it's still a monoprotic. And then H3PO4 is a polyprotic. Kind of the main one was E. I just really wanted you to look at that one because I figured it was tricky. 25, I love true and false questions, so here you go. If the attraction between H negative and A positive is strong, the reaction favors the left and the acid is weak. True or false? True. Well, let's check it out and see why. So we have an attraction between H and A. This is our, did I do the signs backwards? I may have done the signs backwards. Right? No, I didn't. I did this. I don't know. I don't care about the signs. If the reaction is strong, it favors the left. So, oh, this is negative and this is positive. That's why I'm saying they're ions. So H positive and then that's A negative. Off screen, sorry. Okay, thank you. Ions, individuals. And then they become HA. So if the reaction is strong between these two, is it going to favor the left? Did I do this right? Let me go over here. I think I wrote it down wrong. I think I did write it down wrong. Okay. Oh, yeah. No, I did good. So I'm going to go like this. Okay. This is what I'm going to do. True or false? Why? So we have HA plus, if the reaction, a reaction always occurs in what kind of solution? It occurs in water. H3O plus HA negative. If the reaction between these guys are strong, then this is as strong. Okay, if it's completely dissociated, it would be a strong acid. Reactions always favor the weaker acid, so this would be our weaker acid, and so it favors. If it's completely dissociated, it's easy for the HA to become HA positive and HA negative. If the attraction between, did I write this down wrong? They don't want to separate, basically. They like being each other. They like being next to each other. I forget. The stronger the acid or base is, the weaker the conjugate is. So it's going to favor the left because it wants to go back to being ions. It doesn't like. Which one's right or left? I forget. Never mind. Anyways, you guys know how to do it. I've forgotten which ones are right or left, and now I'm confused. So, that next one. Ka, if it's small, the acid is weak. True or false? It's actually true. They have an opposite reaction because how do you get the pKa? Yeah, it's true. Because the Ka is directly associated to the conjugate acid, the actual acid, over the ions. So H negative, A plus. So if this is small, then this has to be really big. And if you have a lot of acids, you're going to have a lot of strong acid, and so it's positive. It'd be really, what? Oh, soft screen, thank you, sorry. The acid's weak. Weak acids do not dissociate, so you want a lot of these guys. If you want a lot of these guys, then you're going to have more than your acid on the bottom, so it's going to have a large number over a small number, so your Ka is going to be large. Does that make sense? It's more of a math question, seeing if you understand an equation, but yeah. So strongly dissociated makes a strong acid, makes a large Ka. Some molecules can auto-ionize. In other words, some molecules can act as an acid or a base with itself. True or false? This is true because water can act like an acid or base with itself, which is something to note. So true. Look at water. Water does this. It turns into H3O and OH negative, either way. And define amphoteric and give an example. Amphoteric is a molecule that can do what? Yeah, it can be an acid or base with itself. Acid or base with itself. And an example would be water, because we just did that. Thank you. Okay, if pKa is large, the acid is stronger. Yes, true or false? This is not true. This is pKa. So it's false. Yeah, false. We just figured out previously that we know when we have ionization, Ha negative, Ha positive, right? We want it to dissociate because that makes it strong, right? So we want a larger this. This is equal to our Ka. Off screen, thank you. This is equal to our Ka, so we want a large number of this. If this is going to be bigger to make a stronger acid, and this is our equation, logarithm of Ka equals pKa, log has an inverse relation with our Ka, so the bigger Ka gets, the smaller pKa is going to be, if that makes sense. And the smaller Ka is, the bigger pKa is going to be. So if we know a large Ka is a strong acid, then we know that pKa is going to be small, if that makes sense. Try it in your calculator. It's kind of fun math magic, but the answer is false. Yes, a large Ka is equal to a small pKa. If you don't know, let's say you forget on the test, I forgot it, plug in values to your calculator to find the logarithmic of 1,000 and then 1, and then figure out what happens. And by that relationship, you should be hopefully able to see for yourself which is which. Write out and balance the equation for the combustion of propane. You should know combustion reactions. They're kind of important. I'm pretty sure there should be somewhere related mentioned on your exam. I would just know all the details. So what is propane? Propane has 3 carbons, so it'd be C3, and then how many H's does it have? So 1, 2, 3. 3 on each tail, so that's 6, plus the 2 from up top, so that's 8, H8, plus combustion reactions always react with what? They give O2. Yeah, I thought you said water for a second. So yeah, they give O2, and then they yield always water, which is what I thought was said and confused. And then the second one would be they always also give carbon dioxide. Yeah, so plus carbon dioxide. So now we need to balance it. C. Okay, so we have 3 C's over here. So we need to transfer that over. And then we have 6 O's plus this one, so that's 7. So we can't really get 7, but we need an even number because we have O2 over here. So let's put down, 4, right? So then we have 4 plus 6, which is 10, which means we need a 5 over here. And then we have 8 hydrogens and 8 hydrogens, so we're set. Balancing is just a lot of trial and error. There's no quick and easy way to do it unless you do it a lot. Practice balancing equations. If you start with 65 grams of propane and 188 grams of oxygen gas was limiting reagent in the theoretical yield, I'm not actually going to do it, but we'll plan it out. We have 65 grams of C3H8. We're going to times that by the molecular weight of propane, and then we're going to get moles. And then we're going to get 1 mole of C3H8 for however many moles of carbon CO2 we want, because we have our previous equation that we went back to that's balanced. So we're referencing that. We get so many moles of CO2. We're going to compare that to, we're going to do the same thing for oxygen. So we have, 188 grams of oxygen. We're going to do the same thing and get moles of CO2. And whichever one has less moles of CO2 is going to 2.85 moles. 2.85 moles over always the bigger number because you're always going to have less in reality than you actually do theoretically. So 3.52 times by 100, you're going to get a number. That would be your percent yield. It should be 81%-ish, hopefully. Okay, if you find the concentration of propane decreases from one molarity to another molarity over 3 seconds, what will the concentration change in oxygen be? You're going to use this equation, rate equals negative change in propane, C3, yes, thank you, over change in time. Your change in concentration is going to be 0.6 over 3 seconds. It's going to be negative, and you should get, this would be, you're going to get a negative value up here. And then you should get 0.2 for your rate. And that would be basically your answer. Yeah, that would be what you would get. You'd want to do the same thing for, that would be the change in concentration for propane, right? So we're looking for the change in concentration of oxygen. Oxygen has a coefficient of 1/5, right? So you're going to take your rate, which is 0.2, and you're going to equal that to the 1 over your coefficient, whatever that may be. Oxygen would still be negative in this case because you're using rate equals negative change in concentration of A over change in concentration of time. And then it'd be that way for all the coefficients, so this is still negative because we're just plugging it into the equation backwards. Sorry. Yes. We're going to put oxygen here now. So we found our rate. We're going to find whatever oxygen is, so it's still going to be negative. So it'd be negative 1/5 over the change in time, which is still 3 seconds, and the change in concentration of O2 is now what we're looking for. Like, we don't know what the change in concentration of oxygen is. If you work out the math, you should get negative 3 moles per liter. You're like, wait, I got a negative concentration, I did something wrong. Not so much because it's in the reactants, and the reactants are going to go away over time, so it makes sense that you have a negative concentration in this case. Does that make sense? This negative? The negative comes from this equation. All the reactants are equal to the equation goes rate is equal to the negative change in concentration. That's a good question, by the way. Thank you. Whatever your reactant is, I don't care. Reactant is equal to the change in time. And so I'm using this equation twice because propane is a reactant, right? And so is oxygen. And so I found our rate, and then I just took that rate, plugged it in. Instead of using methane, I used oxygen, if that makes sense. So our negative is still going to stay there. It only went away because in this value, our change, it's decreasing. It's final minus initial, right? So it's 1.2 minus 1.8. And so we have a negative change in concentration, which again makes sense because we're losing propane as time goes over, as time continues, if that makes sense. Okay. If this reaction is determined to be second order, determine the rate constant if the concentration of propane is 1.8 molarity and the concentration of O2 is 0.34. So we'd want to find out, so the reaction is second order, and we know that you could have one of two reactions. I'm looking for this rate law. Yes, thank you, I'm sorry. C3CH8 O2. You could have that raised to the coefficient of 2 or raised to the power of 2 and this raised to the power of 2, but I want this particular one because I don't tell you specifically in the exam which one it is. And then we know our rate, right? Our rate is 0.2. We don't know what our K is. That's what we're looking for. And so our concentration of propane is 1.8, and our concentration of O2 is 3.4. We do the math, and we should get K is equal to 0.03, 1 over molarity per seconds. You all know how to do the math for this, right? Okay, good. Let's do, how many more do I have? Okay, let's go forwards. Gibbs free energy needs to be, I'm going to skip 35. I'll come back to it if I can, but I only have 20 minutes and I want to get through more concept questions than the math, if that's cool with you guys. Gives free energy needs to be positive or negative to be spontaneous. It needs to be negative. E cell needs to be positive or negative to be spontaneous. Positive. The rate constant needs to be positive or negative to be spontaneous. It doesn't matter. That has no effect on spontaneity, whether or not the rate constant is spontaneous or not. So that's a trick question. A 25, okay, 39. We should probably come back to it. It's a long one. We'll come back to 35 if we have time. I want to go through the quick and easy ones first. Which of the following is the best buffer solution? So, this is a really good question. Okay, so how do we make a buffer solution? What's one of the things we have to look at? We have HCl as a strong acid, and it wants to get rid of its proton, and it wants to go to water. Because it wants to lose its protons, it's going to really readily make our water acidic, and so because it's going to have a great reaction with our water, it's not going to be happy. HNO2, it's also a strong acid. So it's a conjugate base of a strong acid. It's going to have the same reaction. It's going to affect our water. We're not going to like that. I'm going to skip that one because, it's the right answer. And then HF is a weak acid. Great, awesome, it could work. But then Br is a conjugate base of a strong acid, and it doesn't work. So we don't like that one either. Which only leaves us with this one, which is neither a strong acid or it's not a strong acid, it's not a strong base, it's weak in both cases, and so it's not going to readily react with water. It's going to be a really good buffer, and we're going to like C. Because it's not a conjugate acid, or it's because it's not a strong acid or a strong base. Okay, what is the best buffer to use for the solution of pH of 7.4? We want to find the pKa. For this, we know that the pKa, whatever our pKa is going to be, it needs to be within one value of the pH. So we would be looking for either 6.4 to 8.4 is our range. 6.4 to 8.4. And if our pKa falls within there, then we know that that's probably a really good buffer. For this case, if you do the math, C has the best buffer. Make note that this is KB and KB, so you need to do some more kind of crazy math with that, but you guys know how to do that. The change in enthalpy of a reaction is negative 12.2 kilojoules per mole, and the change in entropy for the reaction at 300 K is 56.5 kilojoules per mole. Find the change in enthalpy. Yes. Find the change in enthalpy of the reaction. Find the change in entropy of the surroundings. So the change in enthalpy for the surroundings is delta SR negative delta S system over T. You plug that in, you get negative 12 over 300 K, and you should get 0.041. Change in Gibbs free energy. You want to use this equation and do the math. You should hopefully get, because you'd plug in your delta H for 12, which is up here, and you'd plug in your temperature, which is K, your S, which we just found, which is 0. Right? No, we'd plug in this value. This is our S that we're looking for. That's our systems. And so we would get negative 12.2 minus 300 times by 56.5, and you would get negative 16.962, comma, 962. What is the sign of delta S of the universe? In this reaction, delta S of the system and delta S of the surroundings, both of those are positive. Yes, thank you. Positive. How do you spell positive? P-I-B-O-S-I. Both of these guys are positive. You know that the delta S of the system plus delta S of the surroundings equal delta S of the universe, right? So if both units are positive, then your delta S of the universe is also going to be positive. So delta S of the universe is positive. And then delta H of the universe in this reaction, second law of thermodynamics, I heard it, or first law of thermodynamics is delta H, there's no change And all delta H is conserved, basically, in the first law of thermodynamics, so it's 0 for delta H, which is something to note, your law of thermodynamics. 43, I have 3 minutes. Determine the molecule out of each pair that has the higher standard molar entropy. So which one has more entropy? We have NaNO3 solid and NaNO aqueous. Which one has more entropy? The aqueous one, because it's liquid, it's moving around, it's active. We have phosphorus tetrachloride. Tetra is how many? 4. And then phosphorus pentachloride. How many is penta? 5. And so which one has more molecules? Penta. And so therefore that one has more entropy because there's more stuff going on. Br squared, Br, 2Br and 2I. Which one is more entropy? How do we figure that out? Well, there's the same number of them. And both of them, it's solid gas, it doesn't matter. So what do we look at? We look at the mass. Which one's bigger? Look at your periodic tables if you have them with you. Which one is bigger? I believe I is bigger. So therefore that one, because it is bigger, has a greater molar entropy. What I'm going to do is I'm going to post the answer for these after I go through the math again. I'm going to post the answer for these online under the Google site so that way you guys can go and look at them and check them out yourself. For the most part, that's kind of it. If you have any questions, you can stay. I'll try to answer them in the 10 minutes we have left. Please leave the evaluations. I need to pick those up and gather those. Make sure to sleep. Make sure to not stress, and make sure to eat breakfast. And then that should be it. And you should be good. I wouldn't worry about it. Yeah. Sorry about the math thing at the beginning. That was kind of embarrassing. Okay.